Okay, next talk is by Alireza Nasr-Isfahani from University of Isfahan and IPM, and he's going to talk about cluster algebras generated by projective cluster variables.
Thank you. First of all, I would like to thank the organizer for taking the opportunity to speak in this conference. My talk is based on a joint work with Karin Baur. In this talk, first, I will recall the definition of lower bound cluster algebra and standard monomials, and recall some results, in this case by Bernstein, Fomin, and Zelvinsky. Then I will define the projective cluster variables in acyclic seeds, and I will speak about the subalgebra generated by these projective cluster variables, and also some results about standard monomials in this case. And finally, I will define the projective cluster variables in acyclic cluster algebra. I will speak about the mutations of these cluster variables, and I will speak about the subalgebra of cluster algebra generated by these cluster variables in type A and type A tilde. Let us start with the definition of the cluster algebra. But in this talk, for the simplicity, I will speak about the cluster algebra without the coefficients. But the results of section 1 and section 2 are true for general case. As all of you know, cluster algebra is a commutative algebra generated by the set of distinguished generators called cluster variables, such that these cluster variables constructed recursively via mutations procedure. And this cluster algebra first defined by Fomin and Zelvinsky in this paper. Let's start with the easy example. If you start with this seed with the initial cluster variables x1 and x2 and a quiver of type A2, there is a two-way for mutation for these seeds, mutation in direction 1 and mutation in direction 2. And if you mutate in direction 1, we have a little new seed, which is a mutation of the first seed in direction 1. And again, for this seed, there are two possibilities for mutation in direction 1 and in direction 2. And if we do the same process, we can find all the seeds and all cluster variables. But in this easy example, we can see that there is an exchange relation between the cluster variables. Xm minus 1, xm plus 1 is equal to 1 plus xm for any integer m. And if we start with the initial cluster variables, x1 and x2, we can calculate x3, x4, and x5. And we see that x6 is just x1, x7 just x2. And in this case, cluster variables are periodic of period 5. And cluster algebra, A of sigma in this case, is a subalgebra of field of rational functions generated by these 5 cluster variables. But in general, there is no control on mutation and cluster variables. Bernstein, Fomin, and Zelvinsky defined the lower bound cluster algebra as a subalgebra of cluster algebra generated by initial cluster variables x1 to the xm and the mutation of these cluster variables. In fact, the lower bound cluster algebra is a subalgebra of the cluster algebra generated by n plus 1 clusters, cluster x, x1 to the xn, where the cluster xi is a mutation of cluster x in direction I. If you see in the example, we have two direction for mutation, mu1 and mu2. If in mutation direction 1, we have this seed, and mutation direction 2, we have this seed. So by definition, the lower bound cluster algebra in this case is a subalgebra of cluster algebra generated by these cluster variables, initial cluster variables, and these two new cluster variables. Bernstein-Fomin and Zelvinsky proved the following theorems. They show that the cluster algebra associated to seed sigma is equal to the lower bounds if and only if sigma is an acyclic seed, which means that the corresponding quiver is an acyclic quiver. They also define the monomials in these cluster variables and which called standard monomials if it contains no product of the form xj, x prime j for any j. And they prove that for a lower bound cluster algebra, the standard monomials in these cluster variables form a basis for L of sigma if and only if sigma be an acyclic. So by using the first theorem, this means that for the acyclic seeds, the standard monomials in these cluster variables form a basis for cluster algebra, because in this case, cluster algebra and the lower bounds are equal. So in our example, since a quiver is an acyclic quiver, by the theorem of Bernstein-Fomin and Zelvinsky, we have cluster algebra equal to the lower bound cluster algebra, which is generated by these four cluster variables. Also, by the second theorem, the standard monomials in a cluster variables x1, x prime 1, x2, and x prime 2 form a basis for cluster algebra. And now let's define the projective cluster variables. Let sigma be an acyclic seed, and d1 to the dn be the dimension vector of the indecomposable projective KQ modules, where KQ is the path algebra of the quiver Q. By the Laurent phenomena, we know that any cluster variables has a denominator in the initial cluster variables. So we call the cluster variable xpi projective cluster variables if the denominator of these cluster variables, we have this form, such that the power of xi is just a dimension vector of the indecomposable projective pi in a quiver Q. And if you see in a cluster category, if start with the cluster category C of KQ, which is a orbit category D over F, where D is a bounded derived category of finite generated KQ modules, and F is a composition of tau inverse and sheaf functor, where tau is a Oslander rate in translation. Then by the results of Buan-Marsh, Reinicke, Rate, and Todorov, and also Calderó, Chapoton, and Calderó-Keller, there is a bijection between the indecomposable rigid objects in C and the cluster variables in A. And if we use this bijection, we see that the projective cluster variables is just the phi of pi, where pi is in the indecomposable projective KQ modules. And we defined LP of sigma for the acyclic seed sigma, the subalgebra of cluster algebra generated by initial cluster variables and projective cluster variables. Let's see in a first example. In this example, we see that we have 5 cluster variables. And in this quiver, we have two indecomposable projectives. One of them is P1 is just a simple projective with a dimension vector 0, 1. And the second one is a P2 is an indecomposable projective with dimension vector 1, 1. Then by definition, xp1 is just these cluster variables, because the in a denominator of the this cluster variable we have 0, 1, and xp2 is just this cluster variable. And LP of sigma is a subalgebra of cluster algebra generated by these two cluster variables plus initial cluster variables. Now, in our first theorem, we show that for an acyclic seed sigma, LP of sigma is equal to the cluster algebra, or equivalence cluster algebra generated by initial cluster variables and projective cluster variables. We also called monomials in these cluster variables standard if it is contains no product of the form xj, xpj for any j.
Is your microphone working fine, Stefan?
Sorry? Do you hear me?
Yes. Yes.
Yes.
So we call a monomial in x1, xp1 to the xn and xpn standard if it contains no product of the form xj and xpj. And in a second theorem, we prove that for acyclic seeds, standard monomials in these cluster variables form a basis for cluster algebra. About these two theorems, first I should say that we proved these two theorems for cluster algebra with the coefficients. And if we compare these two theorems by the theorems of Bernstein, Fomin, and Zelinsky, it is natural to ask about the converse of these two theorems. About the theorem 1, we will see that the converse of theorem 1 is not true. But about the theorem 2, we don't know any answer about the converse of this theorem. And if we start with acyclic seed, we have a maximal gradient sequence obtained by mutating X source. And it is easy to see that the cluster variables in this maximal gradient sequence exactly is a projective cluster variables and initial cluster variables. So our theorem shows that for the acyclic seeds, the cluster variables in a maximal gradient sequence obtaining of by mutation of in source generate the cluster algebra. And this is related to the question of Greg Muller, who asked about do the cluster of variables in a maximal gradient sequence or green to red sequence generate the cluster algebra? And this question is open in general. And about the our theorem, Funkin point out that for acyclic seed with the pattern in the language of Kimura and Quinn, the standard monomial basis we introduced agree with the associated dual PVW basis defined by Kimura and Quinn. Also, he pointed out that these standard monomials are important for defining a triangular basis for cluster algebra. And also, these standard monomials form a topological basis in a topology defined by Davidson and Mandel in this paper. Now, let's define a projective cluster variables for acyclic cluster algebra. First, recall that for any cluster tilting object T in a cluster category of C of H, where H is a hereditary finite dimensional hereditary algebra, we can associate the pair T and Q of T called tilting seeds, where Q of T is a quiver of opposite of endomorphism algebra of cluster tilting objects in a cluster category. Now let A be an acyclic cluster algebra. Then by definition, there exists an acyclic seed U and Q prime, such that this seed is a mutation equivalent to the initial seed X and Q, or equivalently, the corresponding cluster algebra are equal. So if we take the C cluster category of the path algebra of quiver Q prime, which is acyclic quiver, and T prime and Q be a tilting seed in this cluster category corresponding to the seed X and Q, corresponding to the initial seed, then we define a projective cluster variables xpi as a P of T prime I, where P is a bijection between indecomposable rigid objects and cluster variables, and T prime I is an indecomposable direct summand of cluster tilting object T prime. For the acyclic cluster algebra, we can find several acyclic seeds, which are mutation equivalent to initial seed, and the acyclic seed U and Q prime is not unique. But thanks to the results of Buon, Marsh, and Rayton, we can show that the definition of projective cluster variables in this case are independent of the choice of the acyclic seed U and Q prime. And similarly, we can define the subalgebra of the cluster algebra generated by projective cluster variables for acyclic cluster algebra. And we denote it by LP of sigma, which is subalgebra of cluster algebra generated by initial cluster variables and projective cluster variables. Now let's see the first example of seed with a cycle. Let sigma be a seed with the initial cluster variables x1, x2, and x3, and Q be a quiver the 3 cycle. An easy calculation shows that xp1 equal to these cluster variables, xp2 and xp3. If we see the cluster tilted algebra corresponding to the this seed, this is the Jacobian algebra of this quiver, and the dimension vector of the indecomposable projectives of this Jacobian algebra is the corresponding the power of xi in a denominator of projective cluster variables. Because, for example, in this Jacobian algebra, the projective cluster variable P, the indecomposable projective P1 has a dimension vector 1, 1, and 0. And we can see that in a denominator of xp1, the power of x1 is 1, x2 is 1, and for x3 is just 0. And we have the similarity for xp2 and xp3. And in this case, an easy calculation shows that the LP of sigma is equal to the cluster algebra. So this example shows that the converse of our theorem is not true. And by the results of Bernstein, Fomin, and Zelvinsky, since in this quiver we have a cycle, the lower bounds is a proper subalgebra of cluster algebra. So in this example, we have a cluster algebra which is generated by projective cluster variables and initial cluster variables, but lower bounds is a proper subalgebra of it. Now we want to study the mutation of these projective cluster variables. If we start with two seeds with the same quiver, but with a different cluster variables, it is known that the corresponding cluster algebra are isomorphic, and this isomorphism given by sending the xi to the yi, and we denote this isomorphism by G. Now let A of sigma be an acyclic cluster algebra such that this cluster algebra generated by initial cluster variables and projective cluster variables. If we mutate the quiver Q in the direction J, what about the cluster algebra with this seed? With the initial cluster variables, but with a new quiver mu J of Q. In this theorem, we show that this cluster algebra generated by cluster variables in cluster X prime, where X prime is the mutation of cluster X in direction J, and new projective cluster variables X P prime 1 to the X P prime M, where X P prime I is a projective cluster variables in this new seed. But in the J place, we have just the J of X Pj. So if we mutate the quiver of the cluster algebra, then two of the generators are changed. One of them is xj, and one of them is xpj. And this theorem is very helpful for proving some more results in this case. By using this theorem, we show that if Q be a quiver, which is mutation equivalent to a quiver of type A, then the lower bound cluster algebra generated by projective cluster variables and the cluster algebra are equal, or equivalent to cluster algebra in this case generated by initial and projective cluster variables. Also, we prove the same result for the case quiver Q is a mutation equivalent to the quiver of type A and tilde. And for proving these two results, we use the classification of the quivers mutation equivalence of mutation equivalence to the quiver of type A. This is a result by Buon and Wante, and then we use the theorem about the mutation, and also use the induction on the number of T cycle in a quiver. Because by this theorem we can open the T cycles and find the generator of cluster algebra, and this help us for proving this theorem. Similarly, for this theorem, we use the classification of quiver mutation equivalence of to the quiver of type A and tilde by Bastian, and use this same idea. And about the converse of the or second theorem, let me back to the example here. About the converse of or second theorem, in our second theorem, we showed that for acyclicities, standard monomials form a basis for cluster algebra. But in this case, in this easy example, we can also define the standard monomials, and we know that the standard monomials generate a cluster algebra. But we don't know if the standard monomial in this case are dependent or not. And this is open up to no. And thank you.
Thank you very much, Alireza. Well, first we thank the talk, the very nice talk from Alireza.
Thank you.
And then, there are any questions, comments? There are questions in the room? Are there any questions? There's not question in the chat. There are any questions in the room? Well, if not, we thank Alireza again.
Okay.
Well, we have 33 minutes break.